Welcome to this video on dynamic memory management in C. In this video, we will explore how to allocate and manage memory efficiently. Let's get started. Understanding memory layout of a C program is crucial for effective memory management, especially when working with pointers and dynamic memory allocation. In the earlier video, we have already discussed the memory layout of a C program, but let's do the quick recap. C program uses five main memory segments: a code or a text segment, data segment, BSS segment, heap segment, and a stack segment. Text segment contains the compiled machine code of a program. It is a read-only segment to prevent accidental modifications during execution. Data segment stores the initialized global and static variables. BSS segment holds uninitialized global and static variables. The system initializes this segment to 0. Heap segment is used for dynamically allocated memory, which is managed manually with functions like malloc, calloc, and free. Stack segment stores local variables and function call information. Let's analyze this code to understand memory layout of a C program. In this code, we have global initialized variable, a static initialized variable, global uninitialized variable, local variable, and memory allocated through heap using malloc function. Can you guess in which segment these variables will go? As we have discussed already, global initialized variables will go to data segment. The static initialized variable goes to data segment. Uninitialized variable goes to BSS segment. Local variable goes to stack segment, and the memory allocated using malloc function goes to heap. This layout plays a vital role in pointer handling, memory management, and preventing issues like memory leaks and dangling pointers. Now let's understand why do we need heap memory. Heap memory provides flexibility. It allows allocation of memory at runtime. Variable size handling. It is useful when the size of an array or a data structure is not known beforehand. Persistence. Memory allocated on the heap exists until explicitly freed, unlike stack variables that are destroyed when the function returns. Avoid stack overflow. For large data structures like graph, matrices, using the heap prevents stack memory exhaustion. Heap memory is a vital in C programming for flexible and efficient memory management. Mastering heap management is the key to building scalable and robust C programs. Let's understand how malloc works and why it is essential for managing memory effectively. The malloc function enables us to dynamically allocate memory on the heap during runtime. It allocates a specified number of bytes in the heap memory. This is the syntax for malloc. It accepts the size as input parameter, which indicates how many number of bytes to allocate, and it returns a void pointer, a pointer to allocated memory. And if memory allocation fails, it returns a null pointer. Malloc requires explicit typecasting. For example, say we want to allocate a memory of 10 integers. The malloc is going to return a void pointer for this allocation. And since we want a memory for a integer pointer, we need to typecast it to integer pointer. The allocated memory block contains garbage values. Now let's understand the basic usage of malloc function with the help of one code example. In this code, we are allocating memory of 5 integers using malloc. First, we declare an integer pointer, and then using malloc, we allocate the memory for 5 integers. Here, size of int ensures that correct size of integer is used. 5 into size of int gives the total size of bytes we need to allocate. As we know, malloc returns void pointer, so we need to typecast it to integer pointer. If memory allocation fails, malloc returns null pointer. Using this if condition, we verify whether allocation succeeded or failed by comparing the result with null pointer. Once memory is allocated, we can access the memory similar to the way we access array. We are using this loop to assign values to a allocated memory, and using this loop, the values stored in the allocated memory are printed. And finally, we free the allocated memory using free call to prevent memory leaks. Let's quickly compile this code and run. Let's run it. Here, as you can see, output is 1, 2, 3, 4, 5. We had assigned these values to the allocated memory using this for loop. And these values are being printed using this loop. This example highlights the power of malloc in dynamically managing memory, allowing flexible handling of data structures. What happens if you access memory after freeing it? Accessing memory after calling free leads to undefined behavior, which can cause crashes or data corruption. Now let's understand what is calloc and how it is used to allocate memory. The purpose of calloc call is to allocate specified number of bytes in the heap memory. The syntax for calloc is this. As input argument, it accepts number of elements and the size of each element. If memory allocation is successful, calloc returns a wide pointer, a pointer to a allocated memory. If allocation fails, it returns a null pointer. Calloc requires a explicit typecasting. For example, this statement allocates size for 10 integers. Here first argument is 10, which is number of elements, and second argument is the element size, which is nothing but size of integer. As calloc returns a wide pointer, we need to explicitly typecast it to integer pointer because we are allocating memory for integers. In case of calloc, the allocated memory block is initialized to 0 and the allocated memory must be freed using free call. This code demonstrates the use of calloc. Here we are declaring the integer pointer and allocating the size for 5 integers. So here the first argument is n, which is nothing but 5, and second argument is element size, which is nothing but the size of integer. This statement does the error handling, and using this loop we are printing the default values of allocated memory, which should be 0, and memory is being freed using free call. After compiling and running this code, we get output as 0. Write this code and try it out yourself. Here is one more question for you. What is the difference between malloc and calloc? The main difference is malloc allocates memory with garbage values while calloc initializes memory to 0. Now let's understand how to free allocated memory and what are the consequences if we don't free it properly. We use free function to deallocate memory and return it to the heap. Just use the free call with the pointer to allocated memory. It is always a good idea to set pointer to null after freeing it. Setting the pointer to null after free prevents dangling pointer access. Now let's understand what is memory leak. In this code we are allocating memory for 100 integers. A memory leak occurs when dynamically allocated memory is never freed. Memory leaks are dangerous. Memory leaks lead to unnecessary memory consumption and performance degradation. Always remember to free memory after its use. Here is one more question for you. What is a dangling pointer and how to prevent it? A dangling pointer is a pointer that points to the memory location that has already freed, which can lead to undefined behavior. How to prevent dangling pointers? Set the pointer to null after freeing memory. Avoid returning of address of local variables from function, because as we know, local variables are stored in stack, and once function call returns, that variable is gone. For null before dereferencing a pointer. Here are some of the best practices for dynamic memory management. Always check for null after malloc or calloc. Always call free after memory usage to avoid memory leaks. Set pointers to null after freeing to avoid dangling pointer accesses. And use tools like Valgrind for debugging memory related issues. Here is one more question for you. Can you return a local array from a function in C? And how can you handle it? Please try yourself and provide your answers in the comment section below. If you found this video useful, please like and subscribe.